region that is completely bounded by y equals root x and y equals x squared. And then we're going to use that region to answer 4 questions. So can we start off by graphing region P? If you need your calculator, go for it. If you don't, that's fine. I'm going to go ahead and just sketch a little picture of region P up here.
Yeah, someone flicked something at me. I was laying down and I was sleeping while he was going over the place, because I know most of it right. And I was kind of sleeping, and then I just something flew by my eyes, and it was like, gray. And I was like, who did that? And no one confessed.
Well, maybe nobody did it.
Yeah,
And also, they're kind of scary.
You guys done with your graph?
Yeah, they're probably scary.
I know.
Okay. So there is my graph of region P right there. Kind of compare a little bit. I labeled my graphs. Hopefully that makes it a little bit more clear. And then I shaded it in there. We can see region P. We're going to rotate this around a bunch of stuff. We're going to start off in A. A says, find the volume of the solid formed when region P is rotated around the x-axis. So I want you guys to just take a minute or two here. See if you can use your Play-Doh and make region P rotated around the x-axis. Make sense? Ready, set, go. Region P rotated around the x-axis. And then we will work to figure out how to find the volume of that solid. You can visualize this. This is similar to what we did yesterday. Kind of turn on its side a little bit compared to what we did yesterday at the end. See if you can do that. I'll do the same thing. It's really important to notice that as you do rotate around the x-axis, and as you saw in your shape, isn't there like a void in the middle? There's sort of it's not a complete hole, but there is like an empty space in there. This is a really important thing for you to consider. Because there's an empty space in the middle there, you've got to use what we learned about at the very end yesterday called the washer method. There's going to be material removed out of the middle. And so once you identify, because there's going to be sort of a hole in the middle there, got to use the washer method. I suggest doing this. Once you say it's going to be the washer method, write this down. Volume equals pi integral big parentheses squared minus little parentheses squared. And we'll decide on the dy or the dx in just a second. But you want to do this. It's easy to mess this up. And if you start off with the right framework of basically pi integral big R squared minus little r squared, you at least have all the things in the right spots. We've got to fill everything in yet, but you got the framework right at least. Next thing, let's decide. Dy, dx. Which one? Why dx? Why is it dx? So we're going around the x-axis, and the representative rectangle has to have what relationship with its axis of rotation? Got to be perpendicular. So the representative rectangle or the representative washer element would be like that. And so the thickness of that is measured on the x-axis. So that makes it a dx thick washer. And so we will put dx on the end. And then the last thing we've got to do is we've got to put the radii in. So the first set of parentheses is going to be for the bigger radius. So that would be for the function that is further away from the axis of rotation. So looking at the graph, your graph, my graph, whatever it is, which function is further from the axis of rotation? Say again? Root x. Yep, on our interval it's root x. And so technically what we'd be doing here, this might not make a lot of sense right now. I'm going to say root x minus 0. And the reason I'm putting a minus 0 in there is because the x-axis has a height of 0 or a y value of 0. And then, of course, the closer function, the smaller radius, would be the parabola. So that would be x squared minus 0. And that would leave us with our final thing to fill in, and that would be the limits of integration. Are the representative disks, or washers in this case, are they going to accumulate from left to right or bottom to top? Left to right. So where are they going to start accumulating? 0. And they're going to stop out here at the intersection point. Do you guys know what the intersection point is? When x is 1. Yep. So this would be our setup. We could solve this one. We could evaluate this one fairly easily. So let's do that real quick. volume equals pi, integral 0 to 1. And if you think this through, because the zeros are just zeros, it would just end up being x squared minus x to the fourth.
It'd just be x minus x. Because you have a root x. So if you
Or x, excuse me, thank you, yes. Sorry about that. X minus x to the fourth. Thinking one step ahead has once again caused me to mess up. So when you anti-differentiate, you get 1/2 x squared, right? So volume equals pi times 1/2 x squared minus 1/5 x to the fifth, evaluated from 0 to 1. And the 0 and the 1 are pretty handy, because when you plug in to do fundamental theorem part 1, volume gives you pi, and you plug in a 1, you get 1/2 minus 1/5 minus 0. It comes down to, can we do 1/2 minus 1/5? What do you get?
I got a third, a 0.3.
Yep, 3/10. Yeah, I agree. So volume equals 3/10 pi, or 0.3 pi, or something like that. So this one would be very doable without a calculator. Others we'd find would be a lot more difficult without a calculator. Some of them might even be impossible without a calculator. This one is pretty doable. Okay, how we doing? Okay, we're going to use the same region, and we're going to go with part B here. I'm going to leave this one more or less entirely up to you. I'm going to give you guys about 3 or 4 minutes to do this. So with part B, oops, let me get where I want to go. Part B, I'm going to retrace that region. It's essentially this all over again. But instead of rotating around the x-axis, we're going to rotate around the y-axis. So if you guys could set up, and if you have a chance, evaluate. If you want to use your calculator to evaluate, I'm fine with that. Let's rotate around the y-axis. That's going to change a lot of how your setup looks, right? Let's see what you do with it based on what we did yesterday. Give you about 3 or 4 minutes to at least, bless you, 3 or 4 minutes to get it set up.
What is the...
This does take a little bit of a different path, but I am hearing that the answer is the same. Let's try to confirm that. So the volume, once you decide again that there's going to be sort of a hole in the middle, the volume is going to equal the washer method, which is pi integral of big R squared minus little r squared, and then we have to fill things in beyond that. So for your setup, did you guys use dx or dy? We've got to use dy here because if we are rotating around the y-axis, we've got to have a horizontal representative rectangle, because the representative rectangle has to always be perpendicular to your axis of rotation, making this a dy thick representative rectangle. So that means dy right here. So that means everything has to be in terms of y. So your limits of integration are still going to be 0 and 1, right? But it's going to be y equals 0 to y equals 1. And then as far as what goes where, the red graph is a parabola, isn't it? Like a regular old function parabola? The red graph? Yes? So now the red graph is the one that's further away, right? And the way we wrote the red graph before was to say y equals x squared. So it would actually be a mistake to do this, right? Why would that be such a mistake? It's got to be in terms of y. So I'm going to erase x squared, and I'm going to say, well, I've got to take this and I've got to convert it over to y's. So I'm just going to square root both sides. So root y would equal x. And so what I would put in there is the distance from the axis of rotation to the red graph is simply root y. And then for the blue graph, which was originally y equals root x, we've got to get this in terms x in terms of y. So we'd square both sides and get x equals y squared. And so y squared would go right here. And you can see at this point, other than the fact that it's y's instead of x's, this is the same setup. So you should get the same answer of 3 over 10 times pi. So, donut creators, Play-Doh players, time to focus a little bit more. This will be different. Okay?
I know how to do it though.
So C says, find the volume of the solid when region P is rotated around the line x equals 3. So this is quite different. It's no longer the x-axis or the y-axis. So I'm going to redraw that region, and we will talk about what that means to rotate around the line x equals 3. Let's try to create this one as well. What kind of a line is x equals 3? It is vertical, yep. I think, guys, we'll just set this one up. We won't take this all the way through to a volume. Okay, so please make this with Play-Doh. I will attempt to do the same thing in the volume. So, of all the ones we've done so far, this one is the most obvious washer method because you can see the giant hole right in the middle, right? So once you identify washer method, again, I encourage you strongly to write V equals pi integral big parentheses squared minus little parentheses squared. We'll decide on the dy or the dx thing in a second. But guys, I'm only giving you this advice because I've seen really capable people make mistakes they should not be making because they didn't set it up the way that I'm telling you to do. I think this will at least get you the right framework. Hopefully you get the details right too. At least this is starting off in the same way every time. Gives you a good chance to be correct. So let's decide, dy or dx, what do you think?
dy.
It's got to be dy. The reasoning behind that is because the representative rectangle has to be perpendicular to the axis of rotation. I just kind of sketched that in there. And of course, horizontal is going to have a dy thickness. And that, of course, sets the course for everything else in this integrand. It's going to have to be in terms of y. Let's go ahead and do the limits of integration next, and we'll save the radii for last. Are these representative washers, are they going to accumulate from bottom to top or left to right? Bottom to top. And so it's going to be y equals 0 to y equals 1. And now we've got to decide on the radii. So the way the radii work is this. We will take our axis of rotation, which is 3. And I'm going to go ahead and, again, I'm trying to make this as, we can talk about why, but I'm trying to make this as like step-by-step as possible as far as trying to help you avoid oopses and forgettings and things like that. We're going to take the axis of rotation, we're going to write 3 minus and 3 minus in those two radii spots. We'll talk about why that is in a second. And then we will put the function that is further away in the first set of parentheses and the function that is closer to the axis of rotation in the second set of parentheses. So which function is further away?
Root x.
Root x, yep. So the blue function was y equals root x. So we got to put this in terms of y. So we would, like before, we would square both sides and we would get x equals y squared. So y squared goes right there. And then in the second set of parentheses, we'll do the same thing, except this would be for the red parabola that was y equals x squared. And so in place of that, we're going to have to square root both sides like we did before. So it's going to be 3 minus root y for that particular radius. You guys understand why that is? It'll be very consistent. It's going to be axis of rotation minus whatever the function is. Does it matter if you did it the other way? What if you did y squared minus 3? Or maybe root y minus 3. Would that matter? Switching the order on a subtraction problem does what? Does the opposite of the answer. Why wouldn't that matter? Because we're about to square it anyways. Think about it. If you have 10 minus 6, you get 4, right? 4 squared is 16. If you do 6 minus 10, you get negative 4. Oh no. But wait a minute, you square it and you get 16. And so I always just go axis of rotation minus function, just to be consistent and not get too worried about the correct ordering in there, because frankly the correct ordering within the radii does not matter because you're just about to square it anyways. Okay, that would be the setup. Do you guys have any questions about that? Okay, we'll do one more, and it's letter D. Why don't you guys flip over to that, and I'll do the same. So exactly the same region, except it is rotated around the line y equals negative 4. So I'll sketch it out again real quick. And again, we're just going to set this one up. We're not going to take it all the way through to the end. So at least try to get a setup. So there's my picture of the region again. Got my axis of rotation, horizontal line y equals -4. It's going to form a pretty similar shape to the Plato that we did earlier. So we're just going to try to set this one up. See how it goes. It's going to be volume equals pi integral big R squared minus little r squared.
So, I have a question.
Hang on, let me finish my little setup here.
Okay.
Do you guys decide, is it dy or is it dx? Dx, because you've got that vertical representative washer, and it's dx thick, so dx goes here. We'll fill in the rest in a second. Your question, Hayden?
So, no matter where your axis of rotation is located, your intervals on your integral will be the same?
Okay, so you said no matter where the axis of rotation is located, the integral will be the same?
The intervals on the integral.
The intervals. Oh, like on the integral from like 0 to 1?
Yeah.
Yeah, because those limits of integration are not speaking about how far away the axis of rotation is. It's saying over which domain or which range will we be accumulating.
Okay.
And so, yeah, so again, it's going to be x equals 0 to x equals 1. That's not going to really change as far as those limits of integration. But of course, the radii will change significantly based on where the axis of rotation is. So the axis of rotation is -4. So I'd go ahead and build this as -4 minus and -4 minus. And then we just need to put the further away function first and the closer function second. So which function is further away? Say again? Root x. Yeah, root x is further away. So that goes first. X squared is closer, and so that goes second. Notice I never said top or bottom. That's very deceptive to say that, because it's not about top or bottom, it's about closer or further away. And depending on where that axis of rotation is, closer or further away could flip. That relationship could completely change. So you want to think of it as which one's closer to the axis of rotation, which one is further away. Yes, ma'am?
also do like 4 plus square root of x?
You could do root x plus 4, which is the same thing you said, because of the minus minus. Yep.
Okay.
Yep. So that's what I said earlier, like you can, within the little parentheses being squared, you can actually flip those around, and it makes no difference. Because all you're really doing is you're finding a change in location,
Right.
and whether that change in location is positive or negative, you're going to square it anyway, so it wouldn't matter. It wouldn't matter. Okay, so there's a setup right there. That's going to be the last washer method we do for today. I think I've got another one built in as a review on Friday, but we'll leave it alone unless you have a question. Okay, so we're going to do one example out of the next section, and we'll do another example out of the last section. That'll probably be just about our time. So let's skip ahead to solids with a known cross-section, and I think we'll skip the first. I think we're going to do example 2 today and for this chapter. We've been doing solids created by rotation. Instead of doing that to finish off, we are going to be doing solids with what we call cross-sections. So there's going to be no rotation that takes place here. These solids are caused by an accumulation or a stacking of cross-sections along a path. And so this requires a little bit of imagination with drawing. So I'm going to try to draw this out for you and show you what I'm talking about when I talk about accumulation. So let's say we had the y-axis. That looks a pretty strange-looking y-axis, right? And the x-axis. What I'm trying to do with that is I'm trying to give you a perspective drawing where the y-axis is kind of going off into the distance a little bit. Does that make sense? Like a three-dimensional, almost like the three-dimensional box we all drew as little kids. The y is going off into the distance. Does that make sense? So what we're going to do is we're going to take various regions. I mean, maybe we could even take the same region that we just were working on a second ago. Let's see what that looks like in perspective. This would be the parabola, right? Make sense? And then the square root would be right here. So that's the same region we were just working with. Does that make sense? So instead of taking that and like rotating it around the y-axis or the x-axis, we are going to vertically stack. It's going to like pop off the page cross sections. You remember this? So the cross sections can take on all kinds of different shapes. They could be semicircles, they could be squares, they could be rectangles, they could be triangles, they could be all kinds of things. So maybe I choose to do like a rectangular square type cross section. Here's what it would look like if I chose to do that. Maybe I'm going to go perpendicular to the x-axis. I will do my best to draw some perspective as to what we're doing here. Does that make sense? Do you see that squarish rectangular popping off the page? That's a cross section. I could draw in some other representative cross sections if I wanted to. Like that one there. They're obviously going to get quite a bit smaller out here on the edge. They get towards the end, bigger in the middle, that kind of thing. You see how that would create a three-dimensional shape? These are pretty hard to visualize sometimes. Sometimes they're even hard to make with the Play-Doh. We'll see how that goes. So let's do this. Let's look at a couple formulas. We'll do one example. That'll allow us to kind of get to the last thing I want to do, and then we'll kind of loop all the way back around and review this again on Friday. So if the cross sections are perpendicular to the x-axis like I just drew, here is the formula. Volume equals integral from x equals a to x equals b. And the integrand is really simple. It's just a of x dx. Let's talk about what a of x means. A of x is the area of each cross section. And you can see from my picture above that those cross sections are potentially going to vary in size. And so not every cross section is going to have the exact same area. And so we're going to have to represent that with variables typically. And then, of course, if the cross sections are perpendicular to the y-axis, it's not going to be a dx thickness, it's going to be dy thickness. So the formula will be exactly the same. Volume equals integral from a to b, but instead of a of x, it'll be a of y times dy. And a of y, again, stands for the area of the cross section. So this is where some really rudimentary geometry formulas will be helpful. Like, do you remember the area formula for a square?
Yeah.
What is it?
Size
Don't say length times width, because the length and the width on a square are the same, right? Side squared, right? Side squared would be the area for a square. Area for a rectangle, base times height, that certainly makes sense. Area of a semicircle, 1/2 pi r squared. So if you know those really basic geometry formulas, those will not be supplied to you. You do have to know the area of a circle. You do have to know the area of a square, a rectangle, a triangle, stuff like that. Okay, so let's skip to the second one, and we'll see how we do with it. Try to visualize it a little bit. We'll do number 4 later. We'll do that next time. So number 5 says, find the volume of the solid formed when cross sections perpendicular to the y-axis are squares, and the circular base, it's got a circular base formed by x squared plus y squared equals 9. Guys, let's draw a quick graph of this. It's a circle base, right? That's pretty simplistic. What is the center of this circular base?
3.
Center is the origin, right? 0, 0. Where does the 3 come into play? That's the radius. So if I was going to try to draw in my circular base would look, in perspective, that's not very good. In perspective, it looks something like that. We are told that the cross sections are perpendicular to the y-axis. So if I tried to sketch those in, they're squares. Now if I tried to sketch those in, they'd look something like this. Now, let's try that again.
Just be a cylinder.
Will, you are totally correct. So Will has already visualized it. If you need to make this out of Play-Doh, you're fine. Will just said it's a cylinder. Sort of. Cylindrical-ish, right? Think this through. Like, it's in the middle, it's going to look very cylindrical, isn't it? But because the cross sections are squares, as you get further towards the edges, like the upper and lower edge of the region, isn't the distance between like the length of the little chord, isn't it going to get shorter? So because it's a square, doesn't the height have to get shorter as well? So this is a pretty challenging one to make, even with the Play-Doh. In the middle, you're going to have the highest point. And then on each edge, it's going to be smaller. So I'm going to draw in a bunch of these little cross sections. Let me try that again. a bunch of these little cross sections that will create this shape. I don't know, if you think you can make it with Play-Doh, go for it. It's pretty tough. It kind of ramps up on each side. It's going to be kind of have a flat surface all the way on the top. It's challenging. Take a minute, see if you can. If you want to try to make it, go for it. It does have some cylindrical-like qualities, though. I agree. I think we'll find parts of this to be pretty easy with one challenging part to get the integrand right. It's cross sections. It just came right out and said it. So I think we can say volume equals. It's just going to be an integral with no pi because we're not rotating anything. Let's set up our dx or dy first. What do you guys think? What is the thickness of each one of these cross sections? Oh, we'll do that in a second. Dy or dx though? Dy, because we're perpendicular to the y, so whatever you're perpendicular to, that'll tell you your differential. So I'll just put a dy out here. And as far as those limits of integration, aren't we going to start accumulating the cross sections down here on the bottom? And we'll stop up there at the top. So I think what Hayden says makes a lot of sense. -3 to 3. Where is she getting the -3 and the 3? Yeah, because the square root of 9 is 3, the radius is 3. So yeah, so -3 to 3 right there. And then what comes down to here in the middle is, of course, the integrand. And the integrand is going to be the cross-sectional area formula. So they're squares. So what's the area formula for a square? Side squared. So I'm going to go ahead and put blank squared. And we got to decide what the side length is. And this is where the challenge comes into play. So take a look at my picture over here. I'm going to use hopefully an easier color to see. You can see the square over there. I'm going to focus on the bottom side. So from right here, I'm putting a blue dot to over here, I'm putting another blue dot. Can you see those? How long is that? 2x. Great memories. Good job. So from the x-axis, from the y-axis over to the right, that would just be x, wouldn't it? But isn't that only half of the length of the square? And so we'd want to put another one over here, making it an x plus another x, making in total 2x. What's the problem with putting a 2x right there? It's got to be in terms of y. So what could I use to replace the x with something that only has y's?
You can solve for x in your original form.
Yep, use the circular base formula to do that. So it's going to be 2 times, I'll just take x squared plus y squared equals 9. And as suggested, we'll solve for x. So that would be x equals square root of 9 minus y squared. And that x that used to be there, I'll just replace it with square root of 9 minus y squared. At this point, it would be set up. Square rooting squared, of course, are just going to cancel each other out. This one would be doable, I think, without a calculator. But we'll forego that for the moment in the interest of moving forward with just one more concept, which we'll revisit on Friday. You guys okay with that part? We'll come back to this. What are you confused about?
Why can't you just call it, like, from there to there, x and not 2x? Why does it have to be 2x?
Because x is measured from the y-axis out to the right or out to the left. That's the definition of x. Like an x distance starts at the origin and goes either right or left. Has to start from the origin. Yeah. Back when you learned like what the rectangular coordinate system was, we always started at the origin and measured right or left or up or down. You always want to use that as your reference point. Okay, so final thing is this. In 7.4, we're going to find out how to find the length of a curve. I'm going to maybe prove it to you a little bit. We'll set up one example perhaps. We'll pick this up again on Friday. So go ahead and move on to 7.4. Okay, so I think you'll find this to be a pretty accessible thing. The formula for arc length, or the formula for think what we're doing here. We're finding the length of a curve. So we're literally saying, take like a parabola, circle, and not find the length of the diameter or the radius, but literally say, if I just travel along the parabola, how far is that? Like how long? What is the length of that curve? It starts with a distance formula, and we'll derive that here in just a second. But I want to show you the formulas first. So arc length in terms of x or arc length in terms of y is going to be the integral from a to b of the square root of 1 plus f prime squared. And it could be either in terms of x or y. But really, honestly, it is just a very formulaic thing. Can I show you a little bit where the formula comes from? Okay, so I'm going to just do this off to the side. We're going to start off with the distance formula that you guys all learned back in like Algebra 1 or Algebra 2. You guys remember? Distance equals? It's the Pythagorean theorem, isn't it? So here's what you probably saw. Square root of maybe like x2 minus x1 squared plus y2 minus y1 squared. Pythagorean theorem, right? Okay, so let's change this a little bit. What if I said distance equals square root of delta x squared plus delta y squared? That still makes sense? Changing x, changing y. So let's talk about how this works with a curve. I'll erase this here in just a second, but with a curve, between any 2 points on the curve, say from right here to right here, how many points are in between those 2 points?
Infinite.
Infinitely many. And so we got to stop thinking in terms of, from this point to this point and say, well, how do we measure the distance between just 2 points an infinite number of times? Aren't we going to have to add up all those little micro distances? So how is it that you add up a ton of little tiny things?
Integral.
Integral, right? A definite integral will allow you to do that. So I'm going to further adapt this and say distance equals square root of, instead of delta x, I'm going to write dx squared plus dy squared. We'll calculasize it a little bit. And then, as suggested, we're going to use an integral. So I'm going to say, well, the distance from a to b equals the integral from a to b of square root of dx squared plus dy squared. As you can see from the formulas, we're getting kind of close, but the question maybe would be, where in the heck does the 1 come from, right? And where does f prime or f prime of x or f prime of y, where does that come from? Here's where it comes from. We're going to take this, we're going to multiply it by a really strategic 1. And here's my 1. I'm going to multiply by dx over dx. So here's how this works. I'm going to leave this dx outside of the square root, and I'm going to multiply the denominator dx into the square root. Let's think about how that works. To get out of a square root, don't you have to square root the thing that's coming out? So to get back in, what do you have to do? Square it. So as I try to multiply this dx in, this denominator of dx, it's going to have to become dx squared, because to come out it would have to be dx. So here's what that would look like. Integral from a to b of square root, it's going to be dx squared over dx squared, sorry about the glare from the window there, plus dy squared over dx squared, and that extra dx is still hanging out outside there. Okay, so to finish this up, what is dx squared over dx squared?
1.
There's your 1, right? There's where the 1 comes from. So if we write that up here, we say distance equals integral from a to b square root of 1 plus, what is dy squared over dx squared? If we wanted to simplify it just a little bit.
F prime squared.
It's dy dx squared, right? Also known as f prime squared. So f prime of x, quantity squared, and then that dx is still on the outside of the square root, the one that we had to begin with. And that's where the formula comes from. It just comes from the distance formula, trying to say, what if we wanted to add up all this infinite number of points in between these two fixed points? That's where we go with it. So I wanted to prove that to you, because when you guys come back on Friday, we're going to jump in and we'll do examples 1 and 2, and then we'll come all the way back around and finish with a couple of cross sections and a couple of washer method, or at least one washer method. Okay? So if you could, put your Play-Doh away, and I will look forward to seeing you all on Friday.